In this video lesson of class 12th physics electrostatics part 2nd, we will learn about the terminology used in electrostatics and other definitional terms, and also about the electrical capacitance and the capacitor. So let us begin with the metals. We all know about the metals. Metals are the good conductors of electricity. Why good conductors? Because they have the free electrons. And these free electrons act as the carriers of the current and are able to conduct the electricity. So metals are such materials which have the free electrons. As far as insulators are concerned, these are the materials which don't have the free electrons in them and are not able to conduct electricity. These cannot conduct electricity because they don't have the free electrons. Definitely some charge carriers is required to carry the current. And also we use this term dielectrics. Now what are the dielectrics? These are the materials which do not conduct electricity, but on applying the electric field, that is, when they are placed in some external electric field. What happens? The induced charges of opposite kind develop on their opposite faces. So, of course, these are the insulators and cannot carry the current, but when placed in the external field, they show the electrical effect. There is a basic difference between the insulator and the dielectrics. Now next, some of the terms, some of the concepts we must remember in the mind regarding the electrostatics of the conductors, and let us have the following points which we should keep in the mind. In electrostatic equilibrium, electric field is zero inside the conductor. That is, inside the conductor, what is there? Electric field does not exist because the charge always resides on the surface of the conductor. We can see this diagram. Here it is, ABCD conductor placed in this electric field between the two plates, right? Then the net electric field within the conductor ABCD is zero. Second point, that electric field just outside a charged conductor. Where? Outside the charged conductor is perpendicular to the surface of conductor. It always remains perpendicular. Here it is. See this conductor is the plus charge, right? And electric field, the plus charge, the electric field outside normal. And when the charge is negative, then definitely normal but inside. For sigma less than 0, that is for negative charge. And that within the conductor E is 0. Another important thing, that V within the conductor is constant throughout the volume of the conductor, right? And that it is equal to that on surface of conductor, right? So net charge in the interior of the conductor 0, and as E is equal to 0, so from Gauss's theorem we have Q is equal to 0, that is charge not to be within the conductor but where it will reside on the surface only. And also that we have seen electrostatic potential constant within the conductor. So V is constant and E is 0 within the conductor. Electric field at surface of charged conductor is given by is equal to sigma upon epsilon naught normal unit vector. Normal unit vector. Outside normal and charge is positive, and towards the conductor, right, inward normal when charge is negative. So these points are very important and we should keep in mind while dealing with the electrostatics of the conductors. Now let us be with the new term, that is the capacitance. Capacitance, every conductor has its capacitance, that is to a certain limit only it can be charged. Just like if we consider some vessel, then we know that up to certain limit we can pour water or any other liquid into this. So amount of the water, volume of the water we can put into some glass, say, right, can be compared as the capacity of that glass. And the water, you can say, be taken as a charge, right, and height or level, that is as much as liquid we pour, water we pour, its height, that is its potential will rise. So capacitance of a conductor in general is nothing but the ability to store the charge, or we can say also energy. That is, we have mathematically this thing as Q proportional to V. More the charge is given, more will the potential of the conductor rise. Or we can have Q is equal to C into V, or C is equal to capacitance of the conductor as Q upon V. We can plot the graph. Definitely it is going to be the straight line between Q and V. For the given conductor, C will be the constant. Now, for a single conductor, it is not enough for us to store the charge on it, so we make some system, and this is known as the capacitor or the condenser. It is nothing but the arrangement of two conductors separated by some distance, very small distance, and kept within the plates as some dielectric medium. This is what we call the capacitor or the condenser. This way we can represent, we can symbolize by the parallel plates, two parallel lines, okay, and when we make onto this arrow, then this is the variable capacitor. So for its capacitance we can have C is equal to Q upon V. This way we can show, having the plus charge and minus charge, uniform electric field within the plates. This is another plate and this is insulated one, right? Some dielectric medium can be placed within the plates, and we can see that the capacitance is further increased. These two plates should be as close as possible. Then the capacitance will be larger.